Good afternoon, everyone. So I'm Dhayalan. I'm a researcher at the School of Engineering at the University of Glasgow, and our large focus on, the focus of our largest area of research is flexible electronics using high-performance semiconductor materials, especially nanostructures of 1D and 2D. And this is a brief outline about my talk here today, briefly explaining the background of the problem and what is the significance of one-dimensional, two-dimensional nanostructures, and why we really care about in the flexible electronics and the core problem involved between bridging the synthesis process using chemical techniques and using them for the flexible electronic applications using very tedious transfer processes, and how a lamination process come into play which has not been explored as a suitable technique for utilizing it in flexible chemical sensors. And then a brief and after the fabrication, I briefly explain about a initial results of the electrochemical characterization, and I conclude with future directions. 1D and 2D nanomaterials are widely being explored, variety of materials explored, and by what I mean by high performance flexible, high performance material is that silicon nanowires, germanium nanowires, gallium nitride, and gallium arsenide, and these are the materials. And we have a rich variety of growth techniques which has been really evolved over 4 to 5 decades, but it's not really been used for the flexible electronic applications, and there are a few bottlenecks for it. So by using these materials in the flexible electronic applications, what we gain is they are obviously we have high performance domain. If you compare them with the organic counterparts, a thin film material, organic materials, definitely the electrical and electronic and physical and chemical properties of these materials are way superior than the organic materials. And even though in one case it will be integrated structures, and discrete structures, and the other one is a 2D layer structure. It's a continuous structure, but both enhances the flexibility and large and conformability. So by gaining these advantages, we will be able to get some attractive applications in the area of robotics and prosthetics. For example, our group's major researchers involved centered on the fabrication of electronic skin and active matrix electronic skin using silicon nanowires. And other applications involved, if you're able to fabricate a flexible physical and chemical sensing, it will lead to wearable systems such as online health monitoring and many systems. So by mean here, the zero-dimensional nanoparticles, it comes in a different domain. It has been explored for many chemical and biological applications, but we are really focused on 1D structures such as silicon nanowires and gallium nitride nanowires and so on, because these are a viable material to fabricate electronic devices such as FETs and other electronic devices. And then 2D materials, and widely explored one was the famous graphene one. Of course, MOS2 is the recently one, but we have bottlenecks in using MOS2 in terms of preparing them in a larger area. I specifically focus on just to motivate with few more works which we have recently carried out in the area of flexible electronics using high performance materials. The first one is we have demonstrated through a customized contact printing setup a silicon zinc oxide nanowire based photo detector on a flexible platform. So I just briefly talk about how that work will related. Different from then onwards, how we move to the work which I'm explaining today. And we have recently demonstrated an energy autonomous e-skin for robotic using a graphene, using a simple hot lamination technique. And high-end application, moving further, the next level of electronic skin will be involved in neuromorphic based electronic skin. Even then, there are nanowires are having potential candidates, to be applied there. So I'll briefly explain the concept of how we can, the size range which we are looking into in the order of 10 to 100 nanometer diameter. And this is a very popular process which has been working for the past 6 decades for the fabrication of silicon or any nanowires basically. So what it does is initially you have a catalyst particle which the size will define the size of the nanowire which we are going to grow, and then after that you take into a high temperature where you expose into the appropriate gaseous sources, silicon or germanium or gallium or aluminum, anything which we want to grow, and then those will decompose only at the specified locations of the catalyst particle and will precipitate preferentially between the catalyst particle and substrate. So what will happen? This initial catalyst size, the choice of the catalyst and the size of the catalyst will decide what the size of the nanowire you want to grow. That's how it works. And this phase diagrams on the right hand side will explain the one key aspect of explaining, because this phase diagram will really tell you what are the process conditions we can really have it for the growth of nanowires. So on the y-axis we have the temperature, where we can clearly see that for high growth rate or high growing wires, we need to really can take the catalyst particle or growth process at slightly, I mean, above 600 degrees centigrade, which is not really suitable for flexible substrates. But this method is really a promising one. The wire which has been produced using this technique are single crystalline, so it has all the interesting all electronic properties. So the SEM image is showing that what I mean, how the catalyst size is particle disposed using a simple dewating technique, gold, and the wires are grown vertically. So the processing conditions which we use it for typically is 600 900 for silicon nanowires. For germanium, around fall in the same range, and we need to use harmful gases such as silicon tetrachloride and silane, and using these conditions. And so it clearly says one point that okay, it's a very promising technique, but to really explore the thing, we need to have a proper transfer techniques to make them use in flexible electronics. And alternatively, we work on one more technique called metal-assisted chemical etching, where we started with this is a top-down method, where it's a very simple compared to that method which explained a bottom-up technique. This technique is really a simple technique, a simple Ebreker chemistry would do to produce the wires in the range of 10 to 100 nanometer. So we take a silicon vapor. So whichever a high-performance semiconductor materials available in the form of vapor, which could be produced as a nanowires in this case. So we pattern it, and on the pattern we just string it to make to allow it to have a kind of mesh structure. So over the patterned spheres, we deposit a catalyst material of in this case gold or silver, and then we remove the spheres from the substrate, and it leave out the mesh structure. So if we then perform the etching process of a simple hydrofluoric acid and H2O2, and it will produce the wires, silicon nanowires, as it's simple. And the similarity between these two processes, like only thing is the wires are attached on the substrate vertically. So we need to for any chemical or any devices or any sensing applications, we need to transfer them onto horizontal platform. That's very important. So uh, we explore at least two processes which have been a promising one to transfer them into horizontal process. The one on the left hand side, a customized contact printing system, because these systems are these are all specifically meant for this process. It's not commercially available. For our purposes, we need to build on our own. It has a horizontal and vertical platform, and the horizontal platform we have a load cell which can detect what is the force at which the the substrate having nanowire is pressed against a substrate which need to be transferred. Which is typically a flexible substrate. I mean, and then we need to control a lot of parameters to have a controlled transfer of nanowires from the donor substrate to receiver substrate. So we need to tune around. So the aligned wires are critical. If it's a mesh structure, we can't really fabricate any active silicon nanowire based devices. So alternatively, one more technique which is simpler than this thing is dielectrophoresis, where we deposit two electrodes, and then we disperse two nanowires into a solution, and then we'll just drop cast into it, and it's electric field assisted alignment will happen between the electrodes, and we can have it. But the problem is not all the nanowires could be processed using this technique, because the nanowires should be in the form of solution dispersed form. That's very important. So synthesis, and we have problem, and we have found with some novel techniques to overcome the synthesis, to use the wires into flexible electronic applications. But these novel techniques really will require only if you need a aligned wires, a controlled density, very controlled wires are needed. But there are many situations where we don't really need to have very controlled aligned structures, where we can have a mesh of structures for flexible substrates, which is well adhered with the substrate. Will that enough? Will it do for the sensing applications? So what we have done is, here we have used a commercial graphene from Graphenia, which could be in a 1 to 5 inch diameter size, and then we have dispersed zinc oxide nanowires, which is grown. We have grown using the technique I explained, vapor liquid solid method. Then we performed a hot lamination process. Then we etched out the copper using iron chloride solution. And after that, the wires are very intact with the surface of the flexible substrate, and we have carried out few testing. And the advantages are it's really we will to transfer at one point. I mean, in a single step process, we'll be able to transfer a large area graphene intact with the zinc oxide nanowires, and it's a very low temperature process and compatible with a large area, and it's suitable for simple applications. And we have grown using zinc oxide nanowires using vapor liquid solid mechanism, where it's a vapor phase transport, where we take a source of graphite zinc oxide powders, and we'll pass the inert gas into it. And as the catalyst placement, it will tend to grow. The wires tend to grow only over the catalyst particle. And these are the images. I mean, SEM and TM analysis for the wires will be grown. And the statistical data saying the thing, what is the size control we have it in this process. And the graphene, this is from the energy previous work which has come from, but it's showing that the hot lamination process is really promising to have a monolayer graphene over large area, which the Raman studies have been proved. And then after the hot lamination process, we characterized the samples, and we found that the wires, there could be plenty of improvement required from this point. But what the point is, the wires are the meshy structures are intact with the substrate. With it's not really it's adhering well with the substrate, and we carried out a early preliminary electrochemical studies because this track we found that it could be used for food monitoring or any meat sensing. I mean, anything you want to analyze in the food. The pH is one of the indicators of the food. So we analyzed the pH of a solution of 3, and in acidic condition we performed it, but we found it the resistance of the internal resistance of between the stack in the electrolytic solution is very high. And we currently were doing it with silicon nanowires dispersed into it, and so we'll be having a different variety of nanowires. So the selectivity will be better for different compositions. And with this, the conclusion directions for this thing, we have demonstrated using a simple process for large area fabrication of a 1D and 2D nanostructures using a simple technique. And it is zinc oxide nanowires as well as silicon nanowires grown using different techniques. And hot lamination provides a promising technique for the applications we are looking into it. And we are currently working onwards to extending this to having a mixture of nanowires to improve selectivity for electrochemical sensing. And I'd like to thank our team members in the Benefit Electronic and Sensing Technologies Group in the University of Glasgow, and our research is funded by EPSRC and European Commission of the Society. And thanks for your attention.